Καλησπέρα σας. Distinguished guests, ladies and gentlemen, on behalf of the Eugenides Foundation, I welcome you to Science and Space Operations at NASA, a discussion with NASA leadership. We are very happy and proud to host two of the most important NASA administrators, Dr. Thomas Zurbuchen, Associate Administrator of Science Mission Directorate, and Mrs. Kathy Lueders, Associate Administrator of Space Operations Mission Directorate. Both will share unique insights into the current and future missions of NASA and reply to audience questions after their presentations. The event is organized by the Eugenides Foundation UTech Lab and the US Embassy in Athens. It will be held in English with simultaneous interpretation in Greek. Before I start, I would like to invite Mrs. Maria Olson, Deputy Chief of Mission of the US Embassy in Athens, for a welcome address. Mrs. Olson.
Kalispera. Thank you, Dr. Kitsonas, for that kind introduction. And thanks to all of you for coming here tonight indoors on this beautiful summer evening for a discussion of something that must have captured the imagination of ancient Greeks who, perhaps not far from here, looked into the night sky and pondered the cosmos. Thanks very much to all the dedicated people who've been working for decades in engineering and on scientific marvels. We can now look to the sky with new understanding. This includes work by our scientists and experts at the US Space Agency, NASA, as well as work done in partnership with nations around the world, including Greece. It's precisely this type of international cooperation that brought together tonight's two speakers to Greece. They're here to attend a conference by the Committee on Space Research, otherwise known as COSPAR. This is the first COSPAR meeting since the pandemic started, and a delegation from NASA is presenting their findings and collaborating with Greek and international counterparts. And their visit really couldn't be more timely. I imagine many of you, like me, were captivated by NASA's release of photos earlier this week, taken by the James Webb Space Telescope. Those photos allowed us to see deeper into space more than ever before, and they provide absolutely stunning clarity. So it's a huge pleasure for me to welcome our two guests who've come all the way from the United States to join us here in Athens this evening. Dr. Thomas Zurbuchen, or Dr. Z, Associate Administrator, Science Mission Directorate, and Kathy Lueders, Associate Administrator, Space Operations Mission Directorate. Really, your visit to Athens allows us to showcase the power of American innovation and what can be achieved through international cooperation in the sciences. We really look forward to hearing from both of you. And I just want to end by saying a word of thanks to our host tonight here at the Eugenides Foundation. Speaking of partnerships in the sciences, the U.S. Embassy has been really proud to work in partnership with you to support the UTech Lab, which I had a chance to tour tonight, which was super cool, and I wish my kids could have taken part in some of the projects there. The lab hosted here in your facilities, and we really look forward to continuing the cooperation that provides training and technology, in science and technology for Greek young people for many years to come. Thank you so much.
I would like now to present shortly our first guest, Dr. Z, as Mrs. Olson said. I will read very few things from his CV from the official NASA site. As NASA's Associate Administrator for the Science Mission Directorate, Dr. Thomas Zurbuchen is tasked with helping us answer some of humanity's biggest questions. Where did we come from? Are we alone? How does the universe work? Dr. Zurbuchen is well versed in the practice of asking difficult questions that help us seek interconnected answers leading to real-world impacts. Growing up in Switzerland, Dr. Zurbuchen pursued degrees in physics, and he has served on and led innovative scientific teams that helped enlarge our perspective on the solar system and the universe. He was also a professor of space science and aerospace engineering at the University of Michigan in Ann Arbor. He was also the founding director of Universities of Michigan Center for Entrepreneurship at the College of Engineering. Dr. Zurbuchen works to ensure that NASA science missions build partnerships across disciplines and with industry and other nations to generate new questions and help advance the frontiers of knowledge and exploration. He brings a wealth of scientific research, engineering experience, and hands-on knowledge to NASA's world-class team of scientists and engineers. Dr. Zurbuchen sets the NASA science strategy and inspires the teams to carry it out. His honors include multiple NASA Ground Achievement Awards, induction as a member of the International Academy of Astronautics and the Swiss Academy of Engineering Sciences, a NASA Outstanding Leadership Medal, and the 2018 Heinrich Greinacher Prize, the leading science-related recognition from the University of Bern. As I said, we can go on and on, but I would like to listen to you, so please, you have the floor.
Thank you. So they said bright blue tie and white shirt, right? Greece? I knew. I got the memo. Look, I'm just so excited to be here with you today, and what I'm going to do mostly is talk to those of you who are younger than me and about the age of my children. And what I really want to do today is kind of tell you that you too could be part of missions like this. You too can be part of an amazing team that does something extraordinary. I'm going to talk to you about space missions, but frankly, what is happening here, you could apply to other things that are really hard. There are things that require more than one person to be successful. The unit behind a successful mission is always a team. It's not an individual, not even the head of science at NASA. That's who I am. It's a team that is there. They have different backgrounds. They come from different environments. They have different strengths. And guess what? Different weaknesses. And together they can do things that, frankly, are almost incredible when you start thinking about it. So you can be part of those teams. That's the first one. I think the second point I want to make here is there's one of the best times you could possibly be in to join if you're so excited what we're doing in space, whether it's here in Greece with the technologies that are being developed, the science that's happening at universities and in institutes alike, but also worldwide. You can join an international community that is locking arms and doing things together across boundaries. I grew up in the Swiss mountains, and I'm currently working at NASA in my job. In my team, there are two other immigrants who grew up in Europe and are there, people from elsewhere, but also, about half of us are women who are in leadership positions in our NASA science team, people who are growing up in environments that are very different than me, and some in big universities, some in small ones, and so forth. So I hope those are the messages that you get today. Teams is what it's about, and think about joining this amazing adventure of space. So I'm doing science, and the first thing you should always ask when people tell you, why should I do that, is what is it actually what science is about? And I want to just explain that to you. And of course, it's something that if you do some history here in Greece, people knew thousands of years ago. And that is that we can learn about nature by observing it. We can learn about nature by observing it, and frankly, looking at the night sky, looking at the oceans, looking at anything we want, we discover that there's laws of nature, secrets of our universe that remain to be discovered. I'm going to show you some pictures at the end of secrets we're just discovering this week. But most of the secrets in the universe, friends, are not yet discovered. Don't listen to people who tell you we know most of the things. That happened many times in history. People said we know everything. They were always wrong. People who tell you that today are wrong. Most of the things in nature that are out there remain to be discovered. Secrets of the universe are not only discovering that, it's not only nurturing what we know, but also how we think about ourselves. I studied physics, frankly, after I heard a class about Copernicus and how he discovered that the sun was in the center of the solar system. And that, of course, was important insight scientifically, but more importantly, changed how people thought on Earth about their own lives. No, the bosses on Earth were not in charge of the whole universe. They were merely on a planet that went around a celestial body they could not influence. And by the way, on a planet in the arm of a galaxy out of hundreds of billions of galaxies, each one of them has hundreds of billions of stars. So very marginal star with a very marginal planet. That's where we are. Secrets of the universe help us understand who we are. By the way, don't think you're small in that universe. Think like the goldfish in the ocean. You're part of something big. That's the message you should take from it. There's one question that's on our minds, and frankly, for thousands of years, people have thought about, and that is, there's one life on Earth. All life here is related. Very deep inside. We learned in the last decades, frankly, only. With the DNA, what's at the heart of each one of us, the plant life, everything, we're related. We have one life. When you look at the stars at night with a child, what's one of the first questions they're going to ask you? Is there life somewhere else? Is somebody observing the other way? Well, we're starting to answer that question in ways that I don't know the answer yet, by the way. I can't tell you that. That would be quite a cool talk, right? We discovered it. No, we're not there. But we can make steps in that direction in ways that, frankly, were not even thinkable 20 years ago. So this is one of the fastest growing fields that we're in. And of course, what we're learning is that the tools we're learning about nature, our own, the most beautiful planet we know, those tools are actually so useful that we're using them every single day. And we're protecting lives, we're saving lives. We had a forecast that you looked at this morning to see how warm it's going to get, in part used satellites from the United States that flew over this country on their way, because we cannot put satellites up in low Earth orbit, and so they stay in one place. Let's talk to the physics teacher why that is. But the point is, we're helping each other with these data. Of course, there's local observations here as well. But the point is, space helps protect lives, helps improve lives on Earth. So that's why we're doing the work we're doing. So everything I'm going to do and show you about has to do with these three questions and three objectives. We're organized by specific topics. Don't get too stuck on it. You're going to see when Kathy Lueders is talking to you about the space station and kind of things we do in space with astronauts. They do experiments, biological and physical sciences is where we're funding a lot of those. So we're deeply working with each other. But of course, we're doing work on Earth, just like I said, all the way to the deep universe and everything in between. Planetary worlds that we're discovering, when you look at them, you think it's fake. It's so amazingly beautiful and different. And yes, it's there. Nature is incredibly wonderful. The way we're doing this is through missions. And I love this chart. Just because it shows all missions. The goal is not for you to read all of these. The only thing I want you to read, though, and I made this joke yesterday, so I'm going to do it again, is basically right at the sun there, you know, at 12 o'clock of the sun, you see that? It's called wind. Most important mission. Why? Why? Because I built the first piece of hardware I ever built in my life, and it's flying on that mission right now. It was a really humbling experience. Oh, your kind of arrogance goes out the door really quickly if you have to learn how to build space hardware, because it's a lot harder than you think, and you needed help. And I was there with the technician, and he taught me how to put the hardware together, because I wanted to build one of these things with my own hands. And it's up there and it's still working. It's looking at the sun right now, today, as we speak. And by the way, there's some other things. And by the way, who cares about me? On that other spacecraft, there were another several hundred individuals who also did their best and basically built it. And each one of those words is a mission. Those in bold-faced are missions that were currently under development. They yet have to launch, and perhaps Kathy's going to talk to you about launching, because she helps me launch missions. But many of the others are there. So look at the 25 missions that are in orbit around the Earth right now. By the way, since last week, it's 26. Because the mission just got delivered to the space station, and they're going to be installing it with a robotic arm that the Canadians built, and we're going to install it on the space station and look from there, looking at dust. Remember when there's dust that is coming up and kind of is in the air? We're going to analyze that specifically with this instrument. So that's what we're doing. I'm going to talk to you about like 4 of those, just to give you some glances of some missions. I could talk, as you can tell, for many hours, and I won't, trust me, because I'm interested in what Kathy has to say. But every year at NASA is a year of science. And just want to tell you what we're doing. This year, you saw that in biological and physical sciences, we're putting some experiment on the space station right now that are focused on biology, kind of life at microgravity, something we're still trying to understand. We're going to talk about the James Webb Space Telescope. You already introduced with that, kind of a good time to talk about that. And this is another year of asteroids, where frankly have a big, these time tablets of our solar system are flying out there, and we want to explore them with these spacecraft. We're going to talk about them, and you see there's a lot of happening at the Earth. I already mentioned one. I could keep going, and I won't. But also, in the next 12 months, we're going to go to the moon 3 times to land and do analysis of our celestial neighbor. I love the moon. I've always wanted to build a mission there because you can look at it at night and make sure it's still there. No. But the point is, I just cool when you see the destination flying in space. Usually kind of the planets that I went to, too small. Mercury, you never see, only in the morning a little bit, So for me, I'm just really excited for this. And of course, so are the hundreds and thousands of individuals that building these missions. There's a lot happening there, and so what I want to do is just tell you like 3 stories and then, frankly, move off here. The first one is about Mars sample return. Remember how I told you that we're interested in seeing is there life elsewhere? The kind of obvious place to look for life is Mars, because it's quite close and it's not hot as hell, as Venus is. Venus is so hot that lead melts on the surface. So it is very, very, very hot. So Mars is a planet that, frankly, looks like a desert, right? I mean, kind of whenever I look at a picture like that, I wonder where the camping trailer is back there, or somebody put up a tent. No, this is Mars, and there's none of that, frankly. But you see your eye pattern matches. It's like, wow, that's a place that used to be wetter than it is today. And frankly, that's exactly what we found looking at minerals and everything. We know now that 3.5 billion years ago, there was water standing on about half of Mars, not all the way 11 kilometers like on Earth, only 150 meters, so it's a lot less. There was an atmosphere that was a lot thicker on Mars. And of course, 3.5 billion years is interesting because during that time, the first life on Earth, like single-cell organisms, started to emerge. So how precious is life? On Mars, with that slightly different environment, can there be single-cell organisms? We know there's a lot of complex chemicals. And frankly, last week was a great week because we picked up 2 samples. We drilled it on the surface in an area where we know now that there was standing water, a dried-out lake bed right there. We picked it up, and we're going to bring it back. We're going to go pick it up end of this decade and then bring it back for the first round trip to Mars. We need to use the best labs to prove if there's fossil life in there, it's in these samples, we believe. So that's why we're doing that. By the way, we're doing this with the European Space Agency, with scientists from around the world that are can get these samples. And I surely hope somebody in Greece, perhaps you, as you grow up and do science, will take some of these samples and prove, perhaps, that there used to be life on that planet, or not. Both is equally interesting, because if Mars does not have that life from the past, life is more precious than perhaps many people think. So that's what's there. By the way, Mars is a horrible place to live. And the InSight Marslander knows that. It's a robotic geologist that is out there, and for the first time has looked below the surface. And you see all that dust that is on the solar panels? Only 40% of the energy is still made with these solar panels because of all the dust that has settled. And frankly, it's going to die soon of cold, because it can no longer heat itself. But the research that's done is amazing. So it has looked on the inside, basically shown that Mars on the inside look a little bit like the Earth. So there's even more similarities than we thought before, but also a little bit different. For example, the earthquakes on Earth are a lot bigger, of course, because we have these continental plates. Mars has none of those. So we know there's fewer of those. What we also discovered there are big impacts from asteroids that hit the planet, and it rings them like a bell or a cymbal in the orchestra. It's like the entire surface is ringing, and we can observe that. So this is the kind of stuff that we do at Mars. Very interesting to go to the moon. And if you want to go to the moon, you say, wow, the Mars rovers look a lot more cool than the moon rovers. See, it's kind of more kind of ugly looking, kind of too high. Well, the reason it looks like this is because we're going to the polar regions at the moon. And so just imagine if you put a rover at the pole of the moon, all the sunlight comes kind of tangential. You see, the sun is not coming from the top. If you're at the pole, right, kind of the sun is coming that way, not that way. On Mars, the sun is coming that way. At the moon, if you're at the pole, the sun is coming tangentially. So you need to put the solar panels really high and vertical, which is why it looks the way it does. What we're actually looking there is we don't think there's life on the moon for many, many reasons. Too young, kind of. But one of the reasons is that, frankly, there was no water, really standing water on the moon, we've proven. But there is water in a way that, frankly, we never knew during the Apollo program, and we're going to prove and kind of figure out whether we can take that water out and actually understand why it's there. So the moon we're going back to with the Artemis program is a moon that's very different than the moon that we left in terms of our understanding. And that's what science is all about. We change how we think. It's not about thinking the same way, always. It's changing how we think. It's about learning. The most beautiful planet we've ever found in the whole universe is our own. It's the planet, of course, where all of us live. Everybody we love is right on the planet, or Kathy would say near the planet, because some of her astronauts are hanging out there, just a few hundred kilometers up. And so what we're doing is we're looking at our own planet and discovering how it works. Now, there's much we have learned. For example, we have learned how water is rising as ice is melting. We have learned how fires, especially in areas that are dry in the western United States, in Australia, even around kind of here, fires are more abundant than they were. But what we've also learned is that the planet is really changing when people are changing. And during COVID, when we turned off, when people left their cars in the garage, we could see it. Now, the good news is some of the pollutants that some of you, my daughter has asthma, these pollutants that give her asthma were not in the air anymore because their lifetime is only a day or so. CO2, the thing we're breathing and that what gives us the greenhouse gas, we barely could see a change, even though no cars were basically driving. Why? Because the lifetime of CO2 is thousands of years. And so the point is that changes to our planet, needs to have a deep understanding, an understanding that we can get from space. The space is the best way to observe our planet, and that's what we're doing with 26 missions as of last week. All right, now I'm going to just go the other way and look at our own universe. And I don't know how you feel when you look at the stars, especially if you're in a place that's such historic significance. And of course, the way I think about it is just, growing up in the Swiss mountains, I thought about it looking deeply and just really feeling that, the sky with its rules, with its beautiful stars and signs, is just magnificent and beautiful. And of course, what I couldn't have guessed as a kid, how big it is. And what I'm looking here at is 5 galaxies. I'm only showing you 4 because I want to talk about something that I need a little bit more zoom. One of them is to the bottom. It's called Stephan's Quintet because it's 5. What you see is these galaxies and how they're interacting, how they're dancing with each other. Especially there in the middle. Do you see the 2 white dots in the middle? Those are 2 galaxies that were separate from each other. And they're getting into a dance with each other and ejecting stars and gas into it. And you see the brownish ejection at the top. There are new stars that are forming there as the old stars that were in that galaxy were kind of dying off, were going through violent transformations. Our universe is full of stories like that. Our own galaxy has gone through things like that in the future. In a long time you don't have to worry about. We're also going to go interact with the galaxy right there. And what we also know in the center of our galaxy, just like those, are these bright things. And they're the indications of black holes. In the galaxies, in the center, are black holes. Things, when I went to school, were theoretical things. We've proven that they're there. In fact, we've imaged black holes, and the one in our own galaxy, not NASA has, other scientists have around the world. And so for me, you look at this, you look at the absolute clarity of this. Each one of those galaxies has hundreds of billions of stars. And by the way, each one of those stars on the average has a planet. And that's what's happening right there. Well, you say, well, how are the stars formed? This is a stellar nursery. I don't know whether you've ever been to a hospital where little babies are born, and that's how it looks in the universe. This slide here took time about 8,400 years or so, the light to come to us. The one I showed you before took 270 million years, so it's a lot farther. This one is in our own galaxy. And you see these brownish clouds out there. They're clouds that are leftovers from previous generation stars, full of carbon molecules the likes of which we're built. And you say, how did our carbon molecules, where did they come from? From that kind of stuff. Environments like this, and you see all these dots there in the brownish area are stars that are being formed right now, not unlike the sun. Many of them don't look like a dot, they look more like a disk because they're planets that are forming with it. So as you look at the star, with a little bit of science, you see full of stories not only of the universe itself, but stories of you. This is a picture book of your past, a picture book of your long gone past, over 7, 8 billion years ago. This is how it all started 4.5 billion years ago when the sun formed. This is how it started. And that's what we're seeing now as we go up there. So what I want to do is really go sit down and listen to Kathy Lueders as she's talking to us about it. But I hope what you get is that sense of wonder. Yes, you can look at the sky with the mind of a person who has a lot of education, but you can also look at the star like a child. And I want to encourage you to do both. Look at nature like a child. And adore its beauty, kind of get a sense of awe from it, and realize how important it is to preserve that nature and, in fact, do the best we can to leave it for the people that come behind us. So, Kathy, how about you?
Thank you very much, Dr. Zurbuchen. Now, I will introduce our next presenter. This is Kathy Lueders. She serves as the Associate Administrator of NASA's Space Operations Mission Directorate, overseeing the International Space Station, the Commercial LEO Development Program, Space Communications and Navigation, Launch Services Program, Human Space Flight Capabilities, and Operations of Crewed Artemis missions. Kathy Lueders previously served as the first female Associate Administrator for the Human Exploration and Operations Mission Directorate, managing the agency's full human spaceflight portfolio. Before joining NASA headquarters, Lueders was the manager of the Commercial Crew Program at NASA's Kennedy Space Center. She began her NASA career in 1992 at the White Sands Test Facility in New Mexico, where she was the Shuttle Orbital Maneuvering System and Reaction Control Systems Depot Manager. She holds a bachelor's degree in Business Administration Finance from the University of New Mexico and bachelor's and master's degrees in Industrial Engineering from New Mexico State University. Mrs. Lueders, the floor is yours.
Oh, Thomas is a hard act to follow. So, okay, well, now we're going to be the toned down portion of the presentation here. So, first of all, I think what we've learned is look at your beautiful city. You know, there's nothing more beautiful than seeing where you live from space. And like Thomas said, it really gives you a great perspective. This was actually a picture taken from the International Space Station from Expedition 9. So if you can understand, we're up to Expedition 67 now. And so we've been having people on the International Space Station for over 20 years now. And we're going strong. We'll be talking about it in a little bit, but we are planning to extend station until 2030. You know, I think it's very important to me and for us to be here today because in a lot of ways, this is where a lot of things began. And we're here, I think Thomas and I are here to kind of have a call for you to continue because we need your help. I think that the international community needs everybody's help across in the world for us to solve big problems we have today. We were able to solve, in this country, solve big problems before that are really the foundation of us being able to do the work that Thomas and I are doing today. But we still have big issues that we need to solve across the board. And so it's really important for us to be able to get all of your ideas and to help us not only do our missions, but really our missions are here to be able to help solve and learn about our planet Earth. So the fun part of my job is Thomas talked about a lot of the things we learn. I'm going to talk about a lot of the things that we put together to learn more. And so really we've been working for the last 60 years to create platforms for our learning. And starting with the Atlas and then going all the way through all the different kinds of platforms that we've developed and deployed instruments off of, developed satellites off of, to be able to put things in space so that we can learn about the Earth and all of the environment around us. You know, Thomas showed this beautiful image. You know, I will tell you, Thomas and I are a team, right? I tell Thomas he needed to launch. He needed to be able to launch, and we have a launch team that actually worked with the Ariane launch vehicle and helped us do the integration to be able to launch that beautiful, beautiful instrument. But even more, we're working today, all the data has to come through our deep space network, which actually has antennas here in Europe and all over the world. It's another place where we would not be able to have communications. We would not be able to bring the data, the critical data down from our spacecraft if we didn't have cooperation around the world with antennas and ground stations for us to be able to bring the data down and be able to collect those beautiful pictures that we've been getting. And this is a partnership. Thomas already talked about it, but the importance of NASA, ESA, the Canadian Space Station, all our ground station support. It's more and more teamwork to make these hard things happen. You know, people always ask us, why are you going back to the moon? But really, we're not going back to the moon. Yes, we're going to the moon as a destination, but we now are going to the moon as an international industry, academia collaboration. And our goal is really to be able to enable, to establish places where we can gain economic benefit with the activities that we're doing, and continue to figure out how to continue to learn and stay and work in deep space. So as I mentioned before, one of my favorite places obviously is the International Space Station. I think it's another place where we've had a lot of teamwork. You know, Space Station today has flown 258 individuals from 20 different countries. It involves over 100,000 people all over the world. Right? Every day I tell people I need a big ticker on the side of the headquarters building as a number of scientific investigations keep increasing, and we're increasing over 3,000 investigations right now. Over 4,400 investigators that are represented. I said before, we're on Expedition 67, and just on Expedition 67, which is a 6-month increment for the cruise, we have 260 investigations alone. And 3.5 million images of our beautiful spaceship Earth have been captured. One of my favorite statistics is we reach over 1.5 million students through different activities with the International Space Station, and continue to look at ways to continue to expand that. This is really an international asset, and we would like Thomas said, this is not for us in NASA, this is not for us in ESA or CSA, it's really for you. We really want you to be able to use our assets that we have out there. And what's become increasingly over the first 10 years of station was assembly and use. The next year's station was us really beginning our scientific experiments. Really the last 5 years and the next 10 years is like fully utilizing it with academia, industry, our continued using our international partners. We have 20 commercial facilities from ESA, JAXA supported ones, and obviously from the United States that are doing research and development and commercial activities on the International Space Station now. And Greece itself has contributed principal investigators or researchers to 11 International Space Station payloads. And so there's lots of ways if you are in academia here today, for you to be able to put in your ideas, work, and interface with our colleagues that are doing science up in the International Space Station. And we are really trying to figure out how to maximize the use. We don't want for the station, when it deorbits in the 2030s, early 2030s, we want to continue to do research and technology development and science in space. And we actually are working with 3 different companies right now to start developing commercial LEO space stations to be able to continue to operate and do research and science and business in space. And then there's Artemis. So Thomas already gave you a little bit of a teaser alert there, but we are going back to the moon. And one of my favorite, Alexandra had asked me on the way over, she said, how did you come up with the name Artemis? And neither Thomas and I could figure out why we came up with Apollo, but we did know how you came up with Artemis, because we're going back to the moon differently this time. We're going back to the moon with women. We're going back to the moon with people that look differently than went to the moon before, and we're going back as a team, as an international team. And so it was very, very important for us to see that yes, obviously Artemis was a twin sister of Apollo and a Greek goddess of the moon and the hunt, but also it's making sure that we see that each one of you potentially can see yourself as a potential person that could go on the moon. And Thomas and I, we didn't go into, really going into doing space right now is a team effort with international collaborations. We also have industry collaborations. Just here and I'll just point out a few of them. We've got we got ESA active dosimeters. We've got, the European service module will be flying. Every single Orion spacecraft is powered by an ESA service module. And so every time you see a crew vehicle, every time you're going to be seeing a crewed vehicle taking our crews up and doing any of our lunar missions, it's a European contribution. And even on the first demo mission, the Artemis 1 mission, which will be uncrewed, but which will be going and orbiting around the moon and really checking out our crew transportation systems, that will be an international event. We are getting ready to do that mission at the end of August. So I want all of you to kind of put that date in there and just keep watching. We're hoping that you can be following along the mission. We'll have lots of information going out about what's going on in the mission during the mission, but you should really feel like that is also a team accomplishment and when we go and do that mission. And finally, I just wanted to end with, we would not be here today without this team. And Thomas and I started our careers, well, maybe for me, I started my career about 30 years ago. I wasn't thinking that I was going to be up here at a podium today. I, went to school. I got a BBA in finance. I discovered I wanted to go back to school after I had 2 young children and got my engineering degree. You can go out there, you can start out and think, I'm not an engineer, I can't do the science, but guess what? You can do it and go back there and do it. We also need all kinds of people. I tell people all the time, I say, we need musicians in space, we need artists in space. One of the most powerful people that we've had has been having an architect help us with the International Space Station so that we can have a better living conditions and be able to make people happier in space when they're there. And architects know how to do that. We need lawyers, we need teachers, we need scientists, we need accountants, most of all. And so we need every single one of you out there. So I tell people all the time, you may not view yourself as a space person, and I'm going to really talk to those of you that are like 18 and under, because you are really, really important for us, because in the things we're going to be having problems with, we need you to help solve this for us. It's not going to be Thomas and me. It's going to be the folks that are out there that are probably like under 3 feet that we're hoping will figure out exactly how we're going to be going to Mars and figuring out how we're really going to be accomplishing these other missions. And it is going to take every single bit of brain power that we have out there to be able to solve the hard problems that we have in front of us, not only here on Earth, but also accomplishing what we are doing out in space. But what we're finding out is as we solve problems in space, they also help us come up with solutions down here on Earth. And there's a cycle of learning and knowledge that we need to continue to grow and work on together to help us all accomplish our important missions. So I really, really appreciate all your time. Thomas and I are here now for questions. Thank you.
Thank you very much. Very inspiring also. I would like to invite questions from the audience now. You can raise your hand and ask a question. Please use the microphone that is somewhere next to you, in front of you. So who would like to ask first a question? Yes? Please use the microphone that is somewhere near there, so other people can hear you also.
Okay. Okay. Seeing as we have been yielded...
A bit more loud.
Okay, so seeing as we have been yielded pictures, images by the James Webb Space Telescope, and seeing as it also has the capacity of investigating the atmospheres of exoplanets, if you find a planet that has an atmosphere that is capable of facilitating human-like life, how will you wish to use that information in your future investigations?
So the first thing I'm going to do if we say that is I'll tell everybody. We'll tell everybody. Look, what we want to do in future investigations for this, like, you know, so where are we, right? Roughly 20 years ago, we thought that only 1 to 5% of stars had planets. Now we know 100% of them have. So it's many, many more planets that are there. We've discovered many planets that are rocky, and they have atmospheres look a little bit like, we have done some initial cuts at atmospheres, but frankly, we had the wrong tool. And as you correctly say, what we can look at is whether these atmospheres could sustain life. So there's only kind of two things we could get from it, right? Kind of the way the tool is built. The first one is to basically show that there are signs in the atmosphere that either are consistent with life, as we had here on Earth when life arose. Frankly, not humans at this point. It's more like single-cell organisms. They really changed the atmosphere of the entire planet. Our atmosphere in our planet is different because of the life here. And so we would look for that. Now, there's one area that we're also looking for that we call techno-signatures. So if there's societies like a place like here in which certain emissions or certain things like relate to technologies that are there, we're of course going to look for that also. So depending on what we find there, the follow-up is very different. On the first type, what we really want to do is build a telescope that's actually there to prove that there's life on there. So it's less just seeing whether the conditions for life are fulfilled, but it's more about really proving that life is there. We're already thinking about that telescope. It's not what we have up there. It just, by the way, I want you to know when we started Webb, there were no exoplanets found. So the exoplanets only came in later, so kind of where we adjusted Webb as best as we could, but we really need to build another tool. If we find techno-signatures, it's an entirely different game. You know, so depending on what it is, how we do follow-up is different. But that's the best answer I know.
Ms. Lueders?
Oh, I was just gonna, I think Thomas's point about we started out with using the instrument in a particular way, and we ended up learning something and then finding out how to better use it. That happens all the time. You know, it happens all the time. So it's really, really important for us to not have our theories in concrete because like Thomas said, we are learning all the time about how is life? How does that work? You know, and how to better be learning and understanding how to be able to learn more. I just think one of my favorite stories is when he started building James Webb, they didn't know how to do some of the things that they were doing. They had to go figure out 10 new things to be able to even be able to put it together. And then it's just such a great story that they originally started it for one purpose and then ended up finding out that you have so many of these other purposes to go. So I really feel like for all of you out here, it's to be able to find that learning that helps us be able to use all of our platforms and instruments even more, right? It's a constant thing. Please help us be able to maximize the use of all of our instruments. When we first started Space Station, we didn't think about how we were going to use it, and we're using it, well, we did think about how we were going to use it, but we are using it today way differently than we envisioned when we went and got funding for it in 1992. So it's really, really important for people to continue to innovate and figure out new ways to be able to use the instruments we have.
Thank you very much. Next question.
If we send so many missions and spacecrafts, But when they finish their mission, what happens with them? Do we left them in space, or do they come back on Earth?
That's a great question. It's actually something that we need to help solve, because in some ways we got to recognize that as we're sending things out, we got to recognize that we may be polluting the environment. And so it's something that we have to think about carefully as we're going out. And I'm hoping one day, one of the experiments that went on the space station just last week had plastic eating worms on it. And it was an experiment from an Arkansas State set of research students. And one of the reasons they wanted to go up there is they wanted to, if they could help us break down plastic on the International Space Station, then maybe there's a way that it would help us with this big plastic problem here on Earth. And so maybe one day we'll have to have one of those spacecraft that starts breaking itself down into the elements so that we're not creating. We'll have to figure out how to work with the lifetime, because we do want to continue to use them. But we do need to think about how do we, as we're going out and as we're doing exploration, we do want to think about how we are doing it mindfully. We have a term called planetary protection, and we think about how do we help the planets that we go and visit, but then also how do we make sure that we also are protecting our planet when we return. But it's a big problem, and we need your help. That's your job, okay? You help us solve this one, okay?
Next question. Yes. The microphone, please, yes.
Hello. As an artist, I'm a singer and a musician, so I listen all of this you say about the planets. What about trying to communicate with many more planets by sounds, by music? What about this part of sound?
It's funny. So when I was a professor in my previous job, I actually spent quite a number of years on that problem. What we've figured out already, we know today that there's certain things we're better at understanding with sounds than with our eyes. Mm-hmm. And so basically by translating data, by looking at data with our ears, you see I'm using the wrong words, by hearing the data the right way, we can actually get a deeper understanding of it. So I've always been very interested in that. Not all problems are that way, so we could prove. I mean, we actually, so that I advised a young scientist who did their doctorate both in the music school and also in science, where I was. And I just think there's a lot of work to be done there. I just kind of, it's kind of our senses, you know, they have served us well, right? Kind of, yes, we see, yes, we have, you know, different senses, but, you know, for how we explore nature, kind of away from our own Earth, generally we don't use our ears, and we can. It's quite a successful way of doing it. And so it's being used, but not enough yet, my opinion.
So it needs maybe progress in this.
I think there's a lot of progress that can be made, kind of really, and learning and iterating, right, kind of, and really developing tools. One of the things that was really exciting to us is also making the nature available to to blind people, kind of to basically, let's give you an impression of that data set. Of course, we also print it in 3 dimensions, so it's going to really use other senses to communicate complex things of the type that are there. I mean, you know, you should compose something with that picture. I think I think it could be very exciting. Frankly, I've been thinking about it when I look at it. You look at the structure, it has different scales that are there. Kind of, music is really great at this.
Thank you.
Ms. Lueders, on that?
You know, as we learn more and more about ourselves, we learn there's reasons why we have these capabilities. There's reasons why a heartbeat of a mother soothes the baby. There's reasons why, you know, crew members that go on the International Space Station bring their guitars and their flutes, and there's this need for music, and it does soothe the soul. And when you're going into space, and sometimes it feels very stark, there's these basic human things, and music is one of them. It's actually, and so how you keep those connections, Thomas was talking about data and everything, but what we find out is even though astronauts don't want to admit it, they're human. And so one of the things that actually helps them, they get woken up with the song in the morning, you know, they get woken up, you know, they play music. We actually, on Voyager, you send out a record with music on it, and so there's reasons why this is inherently a human piece and what makes us, and there's music all around us, right? So we're reason, Thomas talked about we're all connected, and I think those sounds are a reason and show that connection too.
Thank you. Next question, please.
How far do you think we're going to see in the universe's birth with the James Webb Telescope?
That's first of all, you have a great shirt. But secondly, so let's quickly just make sure we look at the age of the universe. So we measured in space what the age is of the universe. I'm not going to tell you exactly how we did it, but just believe me, it's 13.8 billion years old. With very high accuracy, that's what it is, 13.8. So it's not years, 13.8, it's billion years. So it's, you know, 9 zeros, right? Remember? And so basically, what we expect the first galaxies to show up is 100 million years after the beginning, 100 to 300. We actually don't know because we've never observed it. So that is, remember, 13.7 to 13.5, right? So that's how old. The closest we've observed with this telescope already, without even trying, is 13.1. Now, I already read this today, that from our scientists, that they already have candidates that are older, so closer to 13.5. So the closest we can get is kind of around there, because otherwise there's no older galaxies. So we think we can really see the first galaxies. But if you think about it, it just bothers your mind, right? Kind of, that's how long the light from these galaxies has been in the universe, propagating at the speed of light. So 13.1 billion years. And that's where the mind goes a little bit weird, right? Because it's like, that's a long time. That's how long we already see it now. Does that make sense?
Next question.
Okay. Yeah, it has to do about the... Can you hear me? Okay. It has to do about the James Webb images. Are there spots that we do not know yet what they are, or like we don't know what happens in there yet, and we have to find out?
So you're asking just because my voice is a little bit louder than yours. Are there spots in James Webb images that we don't know what's happening? Most of them. I told you a few that I know, and that frankly the reason I know is because I used Hubble Space Telescope images of some of them, and that already were analyzed. And kind of the old galaxies, the ones that he asked about, we only have a handful that we fully analyzed. We just took some of the spots, did a quick analysis for a week, and it's really exciting right now. As we're speaking here 24/7, we're making measurements right now for scientists around the world. The last 24 hours, we took measurements of planetary system called TRAPPIST-1. It has a red star in the middle, and it has 6 or 7 planets. And we took 5 hours of measurements of that in the last 24 hours. And we have no clue what we're going to find. So there is a lot of the work that we don't know yet. Frankly, we're looking at the universe in a totally new light. We've never seen it. We need to learn how to do that. So what I'm doing is I'm showing you things that we have learned, but the vast majority of this stuff, frankly, I've been talking to scientists who are specializing in this. It's like, we need to really learn how to look at these data. Most of the stuff we don't know yet. Is the short answer.
As I understand, we are getting more questions instead of getting answers with the telescopes. We are learning that we don't know things.
Yeah, I think that it's one of those things that about science. You know, like sometimes people ask me, doesn't it make you feel bad that when you do research, you find things you don't know? And, you know, I want to ask you, like, if you were a goldfish, where would you rather live? In a fish tank or in the ocean? I'm an ocean person. I don't want to be in a box that I understand. Around me is like, oh, I hit the glass here. I hit the glass here, and the plant is at 2 in the morning. At 2 in the afternoon, there's food coming because somebody is giving it to me. You know, like, so, I mean, so for me, the more you ask these questions, the more it's there. It's also true, though, that we start learning things, right? It's kind of, yes, there's questions that are coming up, but all of a sudden we can take like 100 of those questions and answer them all at once. And that's what happens sometimes. A new concept arises. And so we kind of move that boundary between what we know and what we don't know back, right? Kind of all of a sudden there's more that we know. But yes, if you're a scientist, and frankly, it can be frustrating at times. If you're a scientist, a practicing scientist, this is what I did for many years, like most of the stuff you try to figure out, you can't figure out. So it's constantly, you try, all of a sudden you find. The first time I found something out that nobody else knew, I remember to this day how I felt. It was 2 o'clock in the morning. I used to work weird times. My wife is here, even weirder than today. So at 2 o'clock in the morning, I figured out something about the sun by myself after many, many months and years of working. That feeling of learning something about nature that nobody else has figured out is it's like you get addicted to it. Like, I want to do it again. Like, where's the next thing? You know, and so for me, I look at these pictures, I'm like, there's so much we can learn and you can figure out for the first time. So that's the feeling I think you'll get once you really start attacking some of these things, start learning about them. And you too can figure out something there. I mean, there's a lot of new data that frankly remain to be understood. And frankly, there's a lot of scientists or citizens that don't have doctorates as of yet, right? That find out things that are really important that we use every day.
Yeah, I think that's one of the great, I love it when Thomas does a presentation and one of the pictures has a name and says citizen scientist, because there's all this data out there and it's really about that teamwork, about people wanting to be part of the science and being there and volunteering their time to be able to look at key pieces of data and help with the tracking and counting and everything else. And there's been so many times where we thought we knew what was going on. Like, Thomas may find out that fact that you thought was right. Somebody else may prove it wrong. So that's the other great thing about it, is you just continue to learn, and we're figuring out the relationships, and those in some cases may be changing over time too. So what's important is that we continue to observe and learn and observe and learn and never be static about it, because each one of us, you know, understands that they're living in a dynamic world and a changing world. And so when you're living in that changing world, you need to be able to continue to learn on how can we change this? How can we make this a better place? How can we learn and solve the problems to be able to do that? Along with how can we just learn more about what is happening in the world to help us then be able to solve those problems.
We will accept one more question from the floor. Yes, please. Yes. Ο νεαρός με την μπλούζα.
So the James Webb Telescope can study the atmosphere of a planet. Is that true?
Yes, it's true. It's of planets within our own galaxy, only those. But there's, 300, 400 billion of those. So only those planets. By the way, the way we do it, I want to quickly explain the way we do it. So you have the star, and it only works for planets that are in the plane. So if you're James Webb Space Telescope, only the planets that go disappear behind the star, like my finger is disappearing from where you're seeing, right? Now, if there's no atmosphere, it's only the geometry of the planet that disappears, right? So it's just a ramp down. And every light, no matter which color, disappears the same way. If there's an atmosphere, the atmosphere just shines through a little bit. The starlight shines through, and depending what's in the atmosphere, some light goes through easier than the other light. So the light disappears at a different time. So we're looking really carefully about how the light disappears and how it appears on the other side. So we subtract off the star and we have the atmosphere, basically the signature of the atmosphere, if you want the fingerprint of the atmosphere. So that's what we're doing, and we're really excited to get started. Again, when we started, we didn't know how to do this. We learned how to do it. And frankly, close to 50% of the work will be focused on that kind of problem, because it's so exciting to so many people for the reason that we already had in the earlier question. Absolutely.
And he's going to need a lot of help. He's got 4 billion of these, right? So he's going to need a lot of help. So you need to go take that math and science and engineering and help him start doing that research so that we can start figuring out with all this data that Thomas is going to make sure is available to everybody.
We'll have one last question that comes from the audience of our planetarium. We will go to the moon, we will go to Mars the following 40, 50, 60, whatever years. Do you have any idea what's the next target?
Well, you know what? I think, remember those people that are under 4 feet tall? They get to help us make that decision, right? Okay. So you guys need to start thinking about that. What's your target? So this woman right here in the green dress, that's your job. You go figure out where we're going to go next, okay? Okay.
So suppose I didn't get any help, which is exactly the right answer. Let me tell you what I'd really like to figure out, and I have no idea how to do it, which is go to the next star and kind of visit planets around another star. And we're a factor of 1,000 off and how far we can travel with spacecraft. So we need to learn how to accelerate spacecraft a little bit faster. We need to learn how to do that, but that's what I'd really like to do in the next
It's going to be some challenge.
Oh yeah, it's very, very hard. I have absolutely no clue how to go about it. But
so let's concentrate on the moon and Mars.
Moon and Mars, that's the easy stuff. Titan would be cool. Oil spill, galaxy, right? Sorry, anyway, sorry.
Okay, thank you very much. Both were very inspiring. Thank you, thank you. I would also like to thank the US Embassy in Athens for helping us organizing the event. Thank you.